This will just be a storytelling video. You won't learn any practical steps for answering questions. For that, skip ahead to the next video. Instead, I'm going to tell you the story of Bayesianism. Bayesianism isn't maths. It's a philosophy, a way of thinking about what it means to know and to believe. Philosophers call this branch of philosophy epistemology. You may be wondering what on earth a video about epistemology is doing in the middle of a lecture course on maths and machine learning. Well, this section of the course is all about how we use our models to draw inferences about the world. And in particular, it's all about how to measure how confident we should be with our answers. Philosophers have spent centuries thinking about epistemology, but by and large, they don't have anything useful to say. It's only since the invention of probability theory, which happened in the 1660s, that we've had the tools to really talk about belief and knowledge. This video is about Bayesianism, which is one school of epistemology. There are lots of people who do the sorts of calculations we'll be discussing without ever thinking about the meaning and interpretation of what they're doing. What I want to try and persuade you of in the next few videos is that Bayesianism is actually a radical philosophy, and if you really take on board its articles of faith, then it will change the way you think. Let me start with a simple example, tossing a coin, the favourite example of probabilists everywhere. We looked at this in the very first section of the course. If you toss a coin n times and get a certain number of heads, your maximum likelihood estimate for the probability of heads is just the obvious fraction. Okay, let's look at an example. Let's suppose person A tosses a coin 4 times and gets 1 head, and says to himself, the next coin will be heads with probability 1 on 4, which is 25%. And person B tosses a coin 12 times and gets 3 heads, and says to herself, the next coin will be heads with probability 3 in 12, which is 25%. Okay, there's something weird going on here. Obviously, B should be more confident than A because she has more evidence. Let's say she tossed 4 million coins and got 1 million heads, then she should be very, very confident. But this word confidence, where's it hiding? If you ask A what his confidence is, maybe he'll answer, I just told you a probability, 25% chance of heads. That's how confident I am. So clearly, knowing a probability is not the same thing as measuring confidence. Here's another example. This is an illustration from an influential paper on adversarial attacks on neural network classifiers. Suppose we've got a neural network that's been trained to classify images. The authors of this paper say that the neural network, when fed the image on the left, gave the answer panda with 57.7% confidence. And then they invented a cunning way to create a very specific noise pattern, like the picture in the middle, so that if you take the panda and add the noise at 7% opacity, then the resulting image looks exactly the same to the human eye, but the neural network says, gibbon, 99.3% confidence. This is obviously worrying if you're in a self-driving car and there's a speed limit sign that says 30 miles an hour, but someone has put in an adversarial attack like this as a sticker over the speed sign, it could fool the car into thinking it's a 70 mile an hour zone. So, the work on adversarial attacks is lovely, but this picture shows a fundamental misunderstanding. What we said from the coin tossing example is that probability is not the same thing as confidence. The neural network that these authors are referring to, it was trained to estimate probabilities. That number 57.7% panda, that's a probability. If you want to know more details about how it was trained, see section 3 of the notes. Okay, thinking about confidence is hard. Let's now turn and see what Bayesians say. We've spent a lot of time on Bayes' rule. Bayes' rule is named after the Reverend Thomas Bayes from the 18th century, and it's a straightforward mathematical theorem that no one could possibly argue with. Bayesianism is something completely different. Bayesianism is the doctrine that says, if there's a belief that we might hold about the world, but we're not certain about that belief, then we should represent the strength of our belief by a number in the range 0 to 1. And furthermore, we should reason about degrees of belief using the laws of probability, all the Venn diagram stuff you learnt at secondary school. Bayesianism was not invented by Bayes. Bayesianism is a school of thinking that's been around since the very dawn of probability in the 1660s and is associated with many names, especially Laplace. We'll come back to Bayes later and see why his name is associated with this school. But let's spell out the Bayesian philosophy a little more. As I said, if we have a hypothesis about the world, for example, that there will be an alien contact by 2050, then we should attach a number to measure our degree of belief in this hypothesis. It's better to use random variables. Let's say the random variable theta is the indicator of alien contact by 2050. Theta is 1 means aliens do contact us, theta is 0 means they don't. Then I might believe probability that theta is 1 is 0.03, or in likelihood notation, the likelihood of the value 1 is 0.03. The thing about random variables is that when we use them, it forces us to think about the sample space, the set of all possible hypotheses, one of which must be true. Random variables also make it much easier to think about hypotheses where there's a continuum of possibilities. For example, in the coin toss example, let's suppose our probability model for coins is that the number of heads is a binomial random variable with parameters n, the number of tosses, and theta, the probability of heads. And let's suppose that we're uncertain about theta. The Bayesianist would say, you should measure your degree of belief in any particular value theta by using a number. And because there's a continuum of possible values of theta, I'll represent my degree of belief by the likelihood of a continuous random variable theta. Likelihoods are allowed to be larger than 1, they just have to integrate to 1 when we integrate over the entire continuum of allowed possible values. Now, let's go through some illustrations of Bayesianist thinking. Here's our coin toss example. The first article of faith for a Bayesianist is that we should represent unknown parameters by random variables, so as to capture our degree of belief in each of the possible values that it might take. Here, the unknown parameter is theta, so that's the random variable we're interested in. The second article of faith for a Bayesianist is that our task is to update our beliefs in the light of evidence. Bayesianists are fundamentally interested in this process, where you start with a prior belief, you see some data, and you update your beliefs to get what's called the posterior belief. The third article of faith is that we have to have a prior belief in the first place. Bayesianists don't care at all what your prior belief is, but they do insist that there's only one correct way to update your beliefs. If you don't have prior beliefs that you can express as a probability distribution, then you're not even worth speaking with, because you're incapable of a rational discussion about what the evidence means for your beliefs. Which brings us to the fourth article of faith. Prior beliefs are subjective. If there are two people both looking at the same probability model, for example a biased coin, then they're perfectly entitled to whatever prior beliefs they want. In this picture, both of our scientists happen to have the same prior belief. They both have a prior belief that theta is a uniformly distributed random variable in the range 0 to 1, but there's no reason at all why their priors should agree. Now we can see the Bayesian answer to our confidence conundrum. Theta is a probability, the probability of heads, but confidence is a way of talking about the distribution of theta. In this case, the top scientist, who only tossed 4 coins, has a spread out posterior distribution, whereas the bottom scientist, who collected more data, has a more bunched up posterior distribution. If we wanted to measure confidence numerically, we could, for example, pick some way to measure the spread of the distribution. We'll go on to that in more detail in the next 2 videos. Let's look at another example to look again at the subjectivity of Bayesianism. In this example that we've just been looking at, both of our scientists had the same prior belief, but in the next example, we'll see what happens when 2 people have different prior beliefs. Let's imagine that we're tossing a coin again, and that this coin is being watched by 2 people, 1 and 2. Person 2 has a preconception that the probability of heads is less than a half. which is expressed by saying that the likelihood is 0 for any value theta larger than 1/2. Now, let's suppose that the coin we're tossing comes out heads every single time it's tossed. After 3 heads, this is what our 2 people believe. And after 10 heads, they've each of them shifted their beliefs, putting more weight on the belief that theta is large. But they started out with different prior beliefs, so they end up with different posterior beliefs. Person 2 had a preconception that it was flat out impossible to have theta larger than 1/2, and there is simply no amount of evidence that can persuade them otherwise. They'll definitely adapt their beliefs, but only within the realm of things that they think are a priori possible. Now, our final illustration of Bayesian thinking. This one will bring in a bit of a computational flavour. We've spent some time in previous videos talking about Monte Carlo sampling. Here it is, as it's done by Bayesianists. Here's a probability model. Let's suppose we have a collection of data points xi, yi, and we think they lie on a straight line, but there's noise, so we've decided to model it as yi is a plus b times xi plus noise for some sensible noise distribution. There are 2 unknowns here, a and b, so as Bayesianists, we'll declare that a and b are random variables. Bayesianists always have to have prior beliefs about their unknown parameters, and a prior belief about a pair AB can be written as a joint likelihood function, PR sub a comma b, open brackets little a little b. Or alternatively, we can just depict the prior belief by generating a sample of AB pairs, and for each pair, draw a straight line y equals a plus bx. Here I've plotted about 100 lines from 100 AB samples. The prior belief that this distribution depicts is that I'm pretty confident the slope is reasonably flat, but I'm pretty uncertain about the intercept. And here's the data, and also the simplest possible straight line fit the maximum likelihood estimators for A and B. The MLE line is a bit steeper than the lines we're predisposed to believe in. So let's see how we'll update our beliefs. Our updated beliefs are a compromise between what we believed initially and what we saw in the data. We've been persuaded by the data that there is a bit of a slope, but there's not enough data here to push us all the way towards the maximum likelihood line. Okay, so this is the general mindset of a Bayesian. The crucial question to answer is, how should we be updating beliefs? This is what we should do. The posterior belief should just be the conditional distribution of the parameters A and B, conditional on the data. Let me repeat that. Bayesians are interested in how we update our prior beliefs in the light of data to get posterior beliefs. And the way they say to do this is simply, our posterior distribution for the unknown quantity should be our prior distribution conditioned on the observed data. This is the only sane thing we could possibly do once we accept the Bayesianist article of faith that unknowns are random variables. Here's a picture we've looked at many times already. The horizontal axis is values of the unknown parameter, let's call it parameter theta, and the vertical axis is possible values that the data might take, let's call the data x. And here I'm showing the joint likelihood of the 2, as well as the marginal for theta. If we've observed the data, if we've seen a particular value little x, then our belief about theta should be this horizontal slice through the joint likelihood plot. In other words, the conditional likelihood of theta conditioned on an observed value of the data x. Obviously, we'll be using Bayes' rule here. That's why it's called Bayesianism, not because Bayes invented the philosophy, but because people who believe in the Bayesianist philosophy use Bayes' rule all the time. This video has been very wordy, trying to explain the philosophy. In the next 2 videos, we'll do some very practical hands-on Bayesianist style calculations.